Swayam Prabha. Digital India. Educated India.
Welcome to the Advanced Digital Image Processing and Computer Vision. We are discussing about the single view camera geometry, and in the last lecture we have considered how a three-dimensional scene point is related to its image point in an optical camera, and this relationship can be expressed in a convenient form as a linear transformations between two space, that is three-dimensional projective space to two-dimensional projective space, or we can say that the three-dimensional coordinate of the scene point in homogeneous coordinate system, which is of the dimension of 4 cross 1, which can be represented as a 4 cross 1 column vector. And just to denote that we are using a convention where a usual three-dimensional point in a 3D coordinate system of real space, there I will be using this tilde over the symbol of the coordinate point expressing the three-dimensional coordinate points, and then that also represents as a column vector, as a sub matrix in the form of column vector of dimension 3 cross 1, and then I am using also the additional dimension for the homogeneous coordinate representation, where the scale value would be 1 in this case, because that expresses also the coordinates of the three-dimensional point in this. And then this is transformed by a projection matrix whose dimension is 3 cross 4 and which provides me an image point. Once again, it is expressed in the homogeneous coordinate system as a 3 cross 1 column vector. So we understand that this image point, if it is expressed in the form of say w into x, w into y, w, then actually this is equivalent to the image point x, y. This is a homogeneous coordinate system. So once you transform, this scale value after transformation may not be equal to 1. That is why I just expressed in the form of this w times of x, which is the scale value which is representing it, just for my convenience. So this is what we discussed, and we have seen various factors of the projection matrix. So various factors of projection matrix in P, and one of the representation I have just shown in this particular title of the slide itself. You can see that P is factored into two submatrices. Actually, I should say components rather of the P. One is a 3 cross 3 matrix, submatrix, which is denoted by M. That's a standard notation I will be following in my representations of P, and this P4, which is a 4th column vector of P. There are other representations also subsequently we will be discussing. Now this column vector is of 3 cross 1 column vector. So just to note some of the features of this projection matrix, the rank of the projection matrix, naturally it cannot be more than 3, and we consider the rank has to be 3 in this kind of mapping. Rank has to be 3, otherwise there would be certain degenerate cases. So rank of projection matrix will be 3, and then the size, as we discussed, that size is 3 cross 4 because it is transforming a three-dimensional scene point in a homogeneous coordinate system to an image point, once again in a homogeneous coordinate system. So you require a transformation from a 4 cross 1 column vector to a 3 cross 1 column vector, and which means that the transformation matrix should be of dimension 3 cross 4 in the matrix multiplication if the dimension matches with those matrix multiplication. Then the degree of freedom, that is number of independent parameters, that is not 12, because you know that in a 3x4 matrix there are 12 elements, but there are actually 11 independent parameters, and this can be very easily seen because if the point P x gives me this x, if I multiply P also with a scale k, that will also give me a point kx, and in the projective space this is the same image point. So, so P and the scaled value of the elements of P, they represent the same projection matrix. That is why now we can express at least all other 11 coefficient parameters of P or elements of matrix P as a proportion to a 12th element. So, there should be number of independent parameters should not be more than 11, but we have seen that actually it is exactly 11, because there are we could relate those parameters also to different imaging parameters related to the imaging system itself. So, once again we will go through, in our subsequent discussions we will have those parameters in our mind. So, so about that, so number of extrinsic parameters, as I was telling in this case, that the degree, they relating those independent parameters to some of the imaging parameters related to the imaging system. So, extrinsic parameters is 6. Actually, this is the parameters which are expressing the coordinate transformation from a world coordinate system with an external reference coordinate convention, externally referenced coordinate convention, to the camera centric coordinate system. So, there would be in the transformation, there would be rotation and translation, rotation of axis or translation of origin. So, for rotation matrix you have 3 parameters, and translation you have 3 parameters. There are 6. And then within the camera itself, there are transformations, because when we have considered a very special simple imaging coordinate convention, which we call canonical convention, there actually you do not have any parameters, because everything has been specified, fixed with that convention, that we consider the image plane should be at a distance of unity, the respective origin of that system would be at the camera center, and also the coordinate axis, 3-dimensional coordinate axis of the scene are aligned to all the coordinate axis of the image is xy, and the optical axis should be normal to the image plane. So, there are so many with so many such constraints, this convention is, this coordinate convention is considered. Now, though these constraints are there, but we understand that several transformations can provide me this kind of configuration. So, those parameters in the imaging system in the camera itself, to make it more general, we have to consider that what are the deviations from those assumptions. So, each one has to be again taken into account for a general situation, such as offset of the principal point. That means your origin of the image plane could be flexibly defined. It is not necessarily it should lie on the principal point, which means principal point is the point of intersection of the image plane and the optical axis. And then the other parameters, focal length is a parameter, but we express them in terms of resolutions, horizontal resolutions and vertical resolutions of the discretization of image points. So, how many pixels per unit length in horizontal directions, and how many pixels per unit length in the vertical direction. So, these two, and then offset also these two, 4, and there is a skew, which means that the coordinate axis, usually it is perpendicular in our convention, but in fabrication of camera, this may be there may be certain error of margin, some error could be there, some deviation could be there, a very small error we allow, and we call it skew, and this can be also taken into account in the expression for coordinate transformation. Now, so these parameters are known as intrinsic parameters, and as I mentioned, these are 5 parameters, and they form a homography matrix which transforms the canonical image points to the observed image points in the camera. So, this is the interpretations of this. Now, if I observe the relationships between the image point and the scene point, that linear relationships, we can find out that there are actually, from these relationships you will get 3 equations, because you understand that this vector is a 3 cross 1 column vector, and this side also finally you get a 3 cross 1 column vector. So, each row of that vector, column vectors, correspondingly expresses an equality conditions which will give us the equations. But we will see that because of this projection, the coordinates of this observed image points, they are related by the scale factors. So, you have one less, you have a dependency among them. So, that is why one dependency, and so from 3 actually there are 2 independent equations, and other equation could be derived from the other 2. This we would like to explore further, but just to understand that if I have only 2 independent equations, then and we can show that they will be linear equations, then let us consider that consider a problem that with some observations, experimental setup, I would like to estimate the projection matrix P. So, how many point correspondences are required there, which means that if I experimentally set up and put a camera at a positions and then define the respective coordinate conventions in my laboratory or in a calibrated setup. So, and say this is my camera position, and I know the respective projection matrix. So this is the camera positions. So, what I can observe only the image points, and then since I know also the respective scene, so I can make a correspondence, because by observing, say for example, this scene point corresponds to this image point, or say another scene point corresponds to this image point. So, each correspondences will give me these 2 equations. So, the question is that how many minimum point correspondences you require to estimate the projection matrix. So, as we have said already that there are 11 independent parameters and there are 2 independent equations. So, you require the minimum number of point correspondences, that number would be 6. So, that is what, but you get an overdetermined set of equations, because you get 12 equations with 6 point correspondences and there are 11 unknowns. So, let us consider this problem of estimation further with this kind of approach. As I mentioned that you have the xi as a scene point and you have the corresponding observed image point, and in general I am also keeping the scale factor wi. So, I will get xi, yi, wi, which means my observed coordinate would be xi by wi and yi by wi. That would be my observed coordinate. So, this should be xi by wi and yi by wi if I consider the coordinates, these coordinates in the observation window. Now, the problem is that this is a problem because you have a scale factor associated with this kind of transformation. So, this equality, because your observations are not with scale factors, when you observe actually the coordinate say xi, yi. So, for which the scale factor is fixed, because this is what is your observed coordinates. So, for every correspondence says they may not adhere to the same same values of elements of P. They are related by scale values, but they are not exactly same values. So, exact equality or hard equality we don't consider while expressing this, while obtaining those equations for hard equality. What we rather consider that, as we know that these are related to the scale. So if I get a pxi, which is a 3x1 column vector, and the observation is xi, so these two should be parallel because they are related by a scale value. So the magnitude is scaled, but direction remains same. So they are parallel. So I will form these equations rather by using the cross product of these two vectors. So if I use a cross product of these two vectors, then I can express the equations in this form, all these three equations in this form. So just let me give you a idea about this. Say we have taken xi, say pxi. Now let us consider the representation of P in the form of its rows. So all the row submatrices. Now the first row I will be writing say R1 transpose, because if I consider row as a column vector, now in the arrangement in the matrix it becomes a row, so the column vector becomes a row. So this is the first row vector, then the second row vector and the third row vectors. Note this transposition is made because all my always vectors are represented as columns. So when they are arranged as a row, then I have to use this transposition. So this is the P, and if I use the pxi, so this can be represented conveniently as R1 transpose, once again the same matrix algebra, R1 transpose R2 transpose xi and R3 transpose xi. So now you have, and you have also the image observation. So let me use the arrow just to denote that this is a vector, and we have taken xi, yi, wi. You consider this representation. Let me clean this part. So you see that this is a vector xi and this. So when I am taking the cross product, so for cross product computations, what I will be doing? I will be considering that computing that determinant and finding out the components along the unit vectors I, j, k, standard our what we learnt in our vector algebra from the basics in our first or second year of our engineering or science education. So we am applying simply that technique here just to show that the mechanism and how these vectors are coming. So if I perform this operation and segregate along I, j, k, so you can see the first component of this vector can be expressed as R2 transpose xi, say wi, minus yi R3 transpose xi. So this is the first component. Then the second component would be xi R3 transpose. So you note the respective notations of capital and upper cases and lower cases here, minus wi R1 transpose xi j. And then we have the third component, which is yi R1 transpose xi minus xi R2 transpose xi k. So what we can write that since this vector should be a 0 column vector, which is 3, so this component should be equal to 0. So this should be equal to 0. Similarly, this component, this should be equal to 0 and this component should be equal to 0. So, from there we get these equations. So, let me write this equation once again. So, what I will do here, I will consider a transpose operation of two vectors. Say if I write a transpose operation, because it is a scalar operation, say consider R2 transpose xi. Now, you know that this is R2 transpose is a 1 cross 4 row vector and xi is a 1 cross 4 cross 1 column vector. So, it will give me a scalar value. It will give me a scalar value, some scalar value. Let me write some scalar value, say S, some scalar value which is of dimension 1 cross 1. Now, since it is scalar value, I can equivalently write it also xi transpose R2. I can write it also xi transpose R2. It will also be the same. So, all these equations I will be writing in a simpler form. So, let me clean my board just to. So what I would be writing, from this component I will be writing in this way, say Wi xi transpose R2 minus yi xi transpose R3 equal to 0. That is the first equation. Then xi R3 transpose xi. So, this is from this one I am doing, minus wi xi. I will what I will write here, as I was, for the sake of convenience, I am writing rather the other way. I am transposing them because of the scalar form, xi transpose R3 and wi xi transpose R1, that is equal to 0. This is the second equation. Then the third equation I will be writing yi xi transpose R1 minus xi R2. Once again, I should use the other convention for my convenience of representing them in a matrix form. So, we will see that why it is so, xi transpose R2 equal to 0. So, let us now consider, let us concentrate on these three equations which we have derived from this itself. Now, if I want to express all of them in the matrix form, that is what we are doing it here. So, once again, let me clean just to give you a better clarity of these writings, and this also I am now cleaning. So, now I am converting these equations, all these three equations in the matrix form. So, what I am considering, these are the unknowns. You see that what are the unknowns? We are estimating P. So, my unknowns are these row vectors or the elements of P, and which I will be representing since we are estimating it. So, they are the variables. So, which I will be again considering as a stack of column vectors of each one. So, this is the column vector of first row, this is the column vector of second row, this is the column vector of third row. So, each one is of dimension, as you see, 4 cross 1, and total dimension would be 12 cross 1. So, these are the unknown. There are 12 elements, 12 unknowns, though we know that actually there are 11 independent parameters. But currently, let us consider this is the estimation process. So, you would like to estimate all the 12 elements in this process. Now, take the first equation. So, what is this first equation? You see that the first component is given as wi xi transpose R2 and minus yi xi transpose R3. Now, here what we are considering, each 0 is a row vector here, 1 cross 4, this defines a submatrix. So, in the matrix algebra, what this first row will be giving? 0 into this. So, we will get 0, 0 into this row vector, column vector. So, this is 0. Then this one into this column vector. So, I can write it as minus Wi xi transpose R2, then plus this one which are all 1 cross 4 column vectors. So, that the total dimension is, here it is, this row is itself 1 cross 12, and this matrix is, as we understand, this matrix would be 3 cross 12 matrix. So, if I multiply this one, it would be yi xi transpose R3, and that equation, that is equal to 0. Now, you observe the first equation, it is the same, only thing is that I have considered the negation of this. So, if I negate it, I will get the same equation. So, similarly, all these equations are expressed in this matrix form, and by inserting the respective 0 row vector, you are basically suppressing eliminating those parameters which are not involved in those equations. So, this is how this is expressed. So, now let us concentrate on this representation. So, you have three equations, but what you can see that in this equation, if I multiply the first equation by xi and then multiply the second equation. So, you just multiply xi cross this first equation and yi in the second equation, and then add them, you will get actually the third equation, once again third equation multiplied by wi. You will get the third row multiplied by wi. So, which means that this row can be expressed as a linear combination of these two, or rather this equation, third equation, can be expressed as a linear combination of the first two. So, this is not an independent equation. So that is why from this set of 3 linear equations, you can simply remove this equation and only take the first equations involving the first row, 2 rows. So, this is this is in a more or I should say in a more detailed way, you can understand that how you can get 2 independent equations instead of 3 equations from the 3 equations. So, we will continue this with that discussion. So, finally, as I said that with a pair of point correspondence, I get 2 independent equations, and then as you understand, you get more, you need, because there are 12 unknowns, these 2 equations cannot solve the problem. We require at least 12 equations, but in this case, since there are 11 independent parameters, we require at least 11 equations. The other coefficients, other parameter could be set to any fixed value and then express all the parameters in terms of that. So, the problem is that you require more number of equations and minimum 6, as I mentioned. So, in our case, for the sake of robustness, what we will consider, we have rather more number of point correspondences, which should be much more than the 6. So, let us consider in a general case, for n correspondences, n is greater than equal to 6. So, this stack of these equations for each correspondence, point correspondence, will form a matrix whose dimension is 2n cross 12, because from each n point you get 2 equations. So, there will be 2n equations, and since there are 12 unknowns in this case, that means this part is 12 cross 1. So, you get 2n cross 12 matrix. So, what you are getting here, you are getting a set of linear equations, overdetermined set of linear equations, and that is also homogeneous, linear homogeneous equations. Now, to estimate these values, to estimate the respective parameters or respective coefficients, what we have to do, we have to use the same direct linear transform method which we discussed when we had discussed estimation of homography, which means we have to minimize this norm AP. Now, P is considered this vector 12 cross 1 vector, and we consider this is normalized. That means the magnitude would be equal to 1, because any solution P will be also equivalent to a solution by a scale multiplied by a scale value K. So, if I know P, I get the respective projection matrix, family of projection matrices, I should say, which are equivalent. So, we have already discussed how we can solve it. It means that in this using direct linear technique, what you have to do, you have to use the A transpose A matrix and then form the eigenvectors. Solve for eigenvalues and eigenvectors. It is the eigenvector for the smallest eigenvalue that would give you the solution. So, that was about this estimation, some technique of estimation. There could be various other techniques. I have just discussed only one algebraic method in this case. Now, let us consider that more about this projection matrix, and here our objective is that from this projection matrix, how we can determine several entities related to the imaging system. So, the imaging geometry. So, here we are considering several different representations. One representation, as I mentioned, the submatrix 3 cross 3, and then the 4 cross 1, 3 cross 1 column vector, 4th column vector. Then the other representations could be as the submatrices of 4 column vectors. Each one is identified by their suffix, by their number, the column number. So, P1, P2, P3, P4, or we have already discussed this representation also, that they are actually represented by again stack of row vectors, where R1, R2, R3 are those row vectors. So, first what we consider that how you can estimate or how you can compute the camera center. So, if I give you just simply projection matrix, through estimation or through some means, that what are the values of the elements of a projection matrix. Then from there, how can you get different geometric entities in that coordinate system? How can we express them? Now, one of the things first we will be considering that computation of camera center. Now, if I consider the imaging configuration, and that in the imaging configurations, the respective say image plane, and for any object, any point, any point say x, if I draw the line that forms that intersection will give the image. I have said it several times just to remind you this factor. But what happens for this center? If I want to take the image of the center itself, now there you can see that you cannot form a ray, because it is a single. So, your definition is this is a line formed from the scene point to the camera center. But if it is the same center, so that line it is the same point, it is not defining any line. So, that is a degenerate case, and we mathematically this degenerate case can be expressed as a singularity, because in that case what will happen, that if I want to take the image of C, which means I multiply the projection matrix with the respective camera center in its homogeneous coordinate system itself, I will get a 0 column vector or null vector. So, in fact, or rather I should say not null vector, I will consider it as a 0 vector, 0 column vector. That this is actually 4 cross 1 column vector. This 0 is a 4 cross 1, because C is 4 cross 1, and when you are doing this should be 3 cross 1 column vector, because you are getting the image point, you are computing image point, but since you will not be able to get it, your scale value would be also 0. So, 0 by 0 gets undefined. That is a singularity. So, if I express the image point, it expresses like this, and which does not indicate any particular value, so undefined value, so 0 by 0. So, this is a singularity, and we call this kind of since this 0 vector, so this C is a right null vector, because if I for any matrix, if this is true, then that becomes a right null vector, and it depends upon the rank of the matrix by which whether what it should be the dimension of the null space, that depends. So you can read the linear algebra, and very interesting subject. I understand many of you already know it, but here only one null vector exists in this case, because rank is 3 in this particular case. So there will be only one null vector, and that is this right null vector in this expression. So here, so from there you can compute the C. How you can compute C? Let us consider that. Say C can be written as C tilde 1. This is a homogeneous representation in our convention. So C tilde is the 3D coordinate of the camera center. So if I use the submatrix representation of the projection matrix, I will be performing these operations C tilde 1. So P into C equal to this, and perform this matrix multiplication, apply the same rule of matrix multiplication, you will get this. When I am equating with a 0 vector, so this will give me that C tilde, I can write it as minus M inverse P4. You can see that I am taking P4 as minus P4, and then M I have to apply the inversion. I cannot apply divisions like that. So the camera center can be computed from the elements of the projection matrix itself. So this is how the camera center is obtained. But when you have a finite, so for finite, if M is non-singular, then inversion is possible. What happens if M is singular? Then the inversion is not possible. Then this expression is not valid when M is singular. In fact, in that case, we will see that the projection mechanism, this fixed point or this center of projection, it cannot be a finite point, where we will mostly see that the camera, in that case, it is a directions that is specifying the camera center. That means projection rays becomes parallel. So the C would be in that case in the form of, say, in the homogeneous coordinate system, the scale value would be 0, which means that this is a direction in the 3 dimension itself. We will again we will discuss it further, clarify these points further. But let us continue with our discussions with other geometric interpretations, with the relating them to the submatrices of the projection matrix. So we will be considering now column representation. So you have these column vectors. So let us consider these column vectors. Now if I use these column vectors, what are their interpretations? So as you know that each column vector is a 3 cross 1 vector, which means they can be represented as a point in the 2D projective space, or can be mapped to some image point. Each column vector would be some image point. And so what are those image points? So let us understand that for which scene points these image points could be obtained. So here it says, summarizes, it's the vanishing point of x, y and z axis. So that means that, say, if you have the external axis, say this is a world coordinate system, this is your origin, and this is your x axis, y axis, z axis, and say this is your camera, you have your camera, and say this is your center. Now this is your, we say this is your center, let the center be in between. So if I consider any point, if I consider any point in the x axis, what I have to do? I have to basically, its image could be obtained by this geometric configuration. Okay. So this is its image. So this is image plane and this it is passing through. So this point, for this point, this is image plane. Now when I am moving towards infinity, what happens? That similarly all my points will be intersecting at some point in the plane, but as it moves to the infinity, we will find that all these points, they are approaching to a particular point which is called vanishing point, because it cannot go beyond that. So more and more you take this, they are basically converging to a particular point, and that is what is the vanishing point of this particular axis, x-axis. So it is a direction. It is any directions. If you consider along that directions, if you move towards infinity, so the image point of that directions will give you the vanishing point. And how do you what is the direction? So this direction x is, the direction of x can be expressed as 1, 0, 0, and the point at infinity in the homogeneous coordinate space would be represented as 1, 0, 0, 0. So if you want to compute the vanishing point, what I have to do? I have to take the image of that point which is at infinity along the x-axis. So this is the point at infinity. If I multiply it with p, then what will happen? You will see that actually you are getting p1, because only the first column vector would be in the resulting operation, only first column vector would be retained, and all other column vectors they don't. So that's why p1 is the vanishing point of this point, or projection of this point, which is the vanishing point along x-axis. In the same way, if I take the y-axis, the point at infinity is expressed in this way. You note that this is the direction ratio of y-axis. So if I multiply with p, I will get p2. And similarly for p3 also, if I multiply with the z-axis, which is again can be represented as 0, 0, 1, 0. So if I multiply it with p, I will get p3. But what happens to p4? As you understand now, if I have a point like this 0, 0, 1 and multiply with p, then I will get p4. But what is this point? Now this is not a point at infinity, because the scale is finite, scale is there, it is 1, scale is not 0, it is 1, okay, it is non-zero scale. So in that case, if I express these coordinates, we will find actually this is what? This is the origin of the coordinate systems. That's why p4 is the image of the coordinate origin. So these are the interpretations of the column vectors. So just to summarize all these things. So you can see that you will get just in a cleaner form I am showing it. So p1 is the image point of the point at infinity at x-axis, which means it is a vanishing point of the x-axis, and similarly for y and z I am not showing them, and then p4 which is the image of the origin. So it just shows that thing. Let us consider the other entities in this imaging geometry. We have already defined what are principal planes, what is the principal axis and principal point. So just to note that, say this is a world coordinate, external world coordinate reference of origin x and y, z, and you have a camera centric coordinate system, which you can derive the camera centric coordinate system for it by using the respective transformations, linear rigid body transformations, that is rotation and translations, rotation of axis and translation of origin, and we have discussed that. And then the principal point is the point of intersections between principal axis, which is the optical axis of the lens in the camera for an optical camera, but we say principal axis, which is the z axis of the image camera centric coordinate system, and then image principal plane is the xy plane of the camera centric coordinate convention. This is the principal plane, and I mentioned z axis is the principal axis. So, how we can actually obtain, say, those quantities, those entities in terms of the elements of the projection matrix. As you know, the plane can be expressed in the form of a planar equation. You know that when we are expressing a plane, I can write the plane equation as ax plus by plus cz plus d equals 0, where xyz is the coordinates of the 3D point. So, all the points which satisfies this equation, and a, b, c, d, these are the coefficients of these equations. So, given a, b, c, d, you define the set of points which satisfies these equations, they form a plane, they lie on a plane. So, that is a thing. So, now if I consider the representation of the plane also in the form of a projective element, we can see that like line, the plane also can be represented by a vector, column vector, which is a 4 cross 1 column vector. And this 4 cross 1 column vector, like the point containment of line relationships, if this is the representation of a plane, I am using say pi to denote a plane. So, for any point which is lying on this pi, it satisfies this equation, point containment relationships, x transpose pi equals 0. It is the similar the line containment relations that is extended in for the 3-dimensional projective space. So there you can see they are orthogonal, x and pi, they are orthogonal, x transpose pi, because that is what is this equation. See, x transpose is x, y, z 1 and pi is a, b, c, d. So, these linear equations can be expressed in this form, or I can also write in this form. This 0 is a scalar value. So, both are expressing my the equation of a plane. So, the summary is that a plane is a representation by a 4 cross 1 column vector. Now, we will see here earlier that we considered the column vectors of projection matrices, and each column vector was of 3 cross 1 representation, which means they are element of a 2D projective space. So, that is why some of the image points are related to some some entities for the imaging systems, those vanishing points and the image of the origin. On the other hand, this row vector representation of the projection matrix, each row is a 4 cross 1 column vector. So, we will be interested to know that then what those rows, because they can also represent a plane. So, considering those rows there as a plane, so what are those planes? What are those planes with respect to the imaging configuration? So, that we are going to discuss now. So these are certain summaries. So, first thing you see that the principal plane, and it is, as we have said, that the definition is plane parallel to image plane. Now, this third row, this itself gives you a principal plane, very interesting. Third row itself is a principal plane, because you know that from the imaging configuration, once again I will be drawing the same thing, like this is the center of projections, it is a camera centric system, and this is your x axis and y axis of the camera centric system, and this is the principal plane. Now, if I have the principal plane, the fact is that if I consider any point in this principal plane, suppose any point is x in the principal plane. So, how do you get its image point? Apply the same rule, draw the projection ray, but since principal plane is parallel, this ray is not going to intersect the image plane at a finite point. What will happen actually if I consider as a parallel ray in these directions, this is the point of intersection of the parallel rays in these directions, that is all, and which means it would be some ideal point in a projective space. So that means the image of that point would be such that its third coordinate, that means the scale coordinate, should be equal to 0. So which gives me this constraint. So if I apply the projection matrix, so if for this point, if I apply the transformation, I will get, at least I know that I will get the scale value as 0, which means if I once again I will reduce it into this form: R1 transpose X, R2 transpose X, R3 transpose X equal to then some values, and then this is 0, which means this forms a constraint. And what is this? This equation is it's a equation of a plane, and this equation indicates that so this is the property. All these points, they have to lie on a principal plane, then only you can get these ideal points as image points. So that is why the third row indicates the principal plane. Now since this is a principal plane, you know that I should consider once again this basic coordinate geometry of 3 dimensions. So this is a representation of a plane, and for a plane you can specify the plane by its normal, which is the direction which is orthogonal to directions of any line lying on that plane. That is the normal. And what is the direction ratio is this normal? We know from our coordinate geometry, they are specified by these first 3 coefficients. Their proportions can give you the direction ratios. And for principal plane, so you see that from R3 transpose X, the first 3 elements of this row vector, that itself will give me. So if I write that 3 row vector in this way, say this is R3, and in a row form, if I write it, so this 3 elements itself will give me the direction of normal. And direction of normal means it is perpendicular to C, so it will give me the direction of the principal axis. So this is the interpretation. Now let us go with the planar, once again the planes. So what happens? R1 transpose X, similar to R3 transpose, if I consider R1 transpose X and if I consider this is 0 and we don't bother about the other 2, so which means your X coordinate of the image point would be 0, which means that in the imaging convention, say this is a, so in the imaging convention, if I consider its coordinate axis, say this is X axis and this is Y axis, now all these points will lie on X axis, Y axis. X equal to 0 means all these points will lie on the Y axis. So this plane will be the plane formed by the Y axis of the image plane. So this is the interpretation that image at Y axis of the image coordinate. So plane containing camera center and the Y axis. Similarly, the other one, this one will give me, that means this is 0, R2 transpose X equals 0 will give the plane defined by camera center and X axis. And the principal point, which is a point of intersection between image plane and the principal axis, this point is the point of intersection along this axis, which means any point at the infinity. So once again, this is the image, this is the vanishing point of this z axis itself. So principal point is the vanishing point of the z axis, but it is not the coordinate z axis, world coordinate z axis which I consider. This is the principal axis. The direction ratio in this case was R31, R32, R33. This is the vectors. So this point at infinity can be represented as R31, R32, R330. In the same way, the direction along this direction, and it is at the infinity. So if I take the respective projections, so I will take this form MP4. This is R31, R32, R330, this will give me M into R31, R32, R33. So this is actually, we say that this vector is MR3. It is a third row, first three elements of third row that represented the column vector. So if I perform this operation, that will give me the principal point. So as you see that, just to summarize how this principal point is computed, we take the third row, and which we are in this case I am expressing as the element of the projection matrix, denoting them as, because it is third row, denoting the projection matrix element as P31, P32, P33, using the row column index convention. And since it is a point at infinity along that direction, it is 0. So the scale is 0. So if I perform the projection of this using P, I will get this expression. So this vector itself is MR3. That is a notation that we are following. That would give us the principal point. Similarly, the principal ray I have already mentioned, that is the optical axis, that is these directions define that direction. But one of the question is that which one is in front of the camera? So what is the view in front of the camera? How do you get that direction which indicates in front of the camera? For that, actually, because both MR3 and negation of MR3 also denotes the same ray. So for this is determinant of the submatrix M, that actually with that sign, and if you take this direction, then that vector itself, that vector indicates the directions in the front of the camera. So with this, let us stop today, and we will continue this discussion again in subsequent lectures. Thank you very much for your patience and listening.